had started a discussion of HPLC, and we had gotten into a discussion of different kinds of ways that particles were made, and we finished with particles and got to the monolithic silica rod. Hopefully you remember that. The only company currently making a silica rod is Merck. That's not the drug company. That's a German company, Merck. And they've been in chromatography for 100 years, almost, it seems. As I said, the advantage of the monolith is that they have relatively low pressure drops, and they have rather high porosities. They have very high interstitial porosities, which makes the pressure drop low. And the advantage of a low pressure drop is that you can make a longer column at a given maximum pressure, so that you can essentially generate more plates. And that, in my mind, is the chief advantage of the monolithic rod. If you look at the literature, you're going to find a lot of people saying, ooh, the monolithic rods are really good for high-speed chromatography. Wrong. It is not true. And a number of people are now saying that that simply isn't true, but they are good for generating a lot of plates. A lot like an open tubular column in GC is good for generating a lot of plates, because we can make those GC open tubular columns 50 meters or 100 meters long, and you can, just really go crazy making plates, which is good. There are other kinds of materials besides silica that have been used to make monoliths. They're predominantly synthetic organic polymers like polymethyl methacrylate, which are functionalized to make them behave like reverse phase supports or behave like normal phase supports. But they can't take as much pressure as the silica rods. You can't make them as long. The mass transfer characteristics aren't quite as good as silica, so they haven't caught on big time. But definitely the monolithic rods have caught on fairly big time. I don't know what percentage of the market they are, but it's not trivial. Okay, so this is really not a bad picture or drawing of what an actual porous spherical silica particle looks like, a fully porous silica particle. The entire particle is porous. You can get by diffusion, certainly not in a straight line, but by diffusion you can get from the outside of the particle all the way to the center, and then move through the entire particle. The stationary phase is located on the inside of the particle. The ratio of the outside surface area, the circumference of the particle to the inside, is minute. You just don't even have to worry about the amount of retention that's taking place on the periphery. It's all inside. With something that has pores on the order of 60 to 80 angstroms, silica will have an enormous surface area on the order of a couple of 100 meters squared per gram. Okay, so this room is about, I'd say 10 meters by 10 meters. So this would be 100 square meters. And you'd have 3 times our square footage in 1 gram of particles. And you could put 1 gram of particles in about a 15 centimeter by 4.6 millimeter column. So you've got a heck of a lot of surface area in that little bit of space. And all that retention is inside the particle. Okay, now we're going to have to start talking, since 90% plus of all HPLC is done on silica, you need to know something about the surface chemistry of silica. So, if you take what we call a fully hydrated silica, and you get that by taking silica and cooking it up in acidified water. Something like 1 molar sulfuric acid, 1 molar hydrochloric acid, something on that order. What happens is you'll break a lot of Si-OSi bonds on the surface of the silica, and they form these kinds of functional groups. This is called a silanol group. SiOH is a silanol group. If you want a rough idea of what the organic chemistry of a silanol group is, it's like an alcohol. But it's somewhat stronger acid in a Bronsted sense than a carbon OH group, right? Carbon, silicon, right below carbon. That SiOH group is a good bit more acidic than a COH group. But there are quite a few different kinds of surface silanol groups. This one here, where the OH group is not near another OH group, is called an isolated silanol group. A silicon atom in the surface that has 2 OH groups on it, that's called a geminal or twin silanol group. It's chemically different than an isolated silanol group. And then if the OH group on the Si is close enough to a neighboring SiOH group to hydrogen bond, that's called a vicinal, which means neighboring. And the hydrogen bonding, the inter-OH group hydrogen bonding, changes the chemistry of the OH group. So we have at least 3 different kinds of chemical reactivities on the surface of silica. That means we're dealing with a pretty complicated surface. And this is actually a rather polar material. It's a very good material for doing normal phase liquid chromatography. In fact, it's one of the major materials used for normal phase liquid chromatography. If you want to do something besides normal phase, you have to chemically modify the surface. The chief form of HPLC is what we call reverse phase liquid chromatography, where we use a surface which is fairly nonpolar. So we have to do something to the surface of the silica to make it nonpolar. And what we do we make believe that this is the silicon atom that's embedded in the surface. We react this OH group with something. And one of the major somethings, actually what's proven to be the best something, is a monochlorosilane. Under the right conditions, which means the right solvent, the right catalyst, right temperature, this OH group reacts with that chloro group and we form a siloxane bond. This bond is a pretty stable bond, really. The fact is that we use these materials in water at relatively low pHs and relatively high pHs, and this bond hangs together unless you abuse it. And abusing it means going to too low of a pH or too high of a pH, or running it at temperatures above 60, 70, 80 degrees centigrade, and then this SiOH bond will hydrolyze. You'll go back to a silanol. The other end of the molecule picks up an OH group and floats off your bonded phase and out the end of the column, and sooner or later the column dies. The so-called catalyst, yeah.
Are R1, R2, and R3?
They're functional groups. Okay, we'll get into the details of R1, R2, R3 as we proceed. For the time being, if you want to think of them this way, R1 generally equals R2 equals a methyl group, and R3 is something else. It could be a C8 group, it could be a C18 group, it could be a propyl cyano group, it could be some kind of fluorinated ligand, all sorts of things. The catalyst here plays two roles. This reaction, when this reacts with that, you generate hydrochloric acid. And like any organic ether reaction, ether-forming reaction, or any organic ester-forming reaction, it doesn't go all the way to completion. And so if you can pull on it by sucking up that acid, you can make it go further to completion. So typically the catalyst is a base of some sort. But it has been proven that the base, something like pyridine, or dimethyl, I'm sorry, no, I didn't mean that, dimethylamminopyridine, is also a catalyst. What happens is some kind of intermediate salt forms between the amine catalyst and the chlorosilane. The chloro group either goes away, or the silicon becomes pentavalent, far more reactive, and it hits that surface silanol and it reacts very quickly. So it's a catalyst, but it's also an acid scavenger, and it pulls the reaction more to completion. So that's one way it's done. Yeah.
So does that mean the catalyst is consumed because it's picking
The
up
catalyst is consumed because it's gobbling up hydrochloric acid. So it is a catalyst, but it also is a base scavenger. Organic chemists do this sort of thing all the time. So this is probably the most common way to do things now. In the early days of HPLC, people used trichlorosilanes. In other words, that was a chloro, that was a chloro. Now these molecules are exceedingly reactive. You open a bottle of this stuff even in Minnesota outside with zero humidity out there, and you'll see hydrochloric acid coming off of it like crazy. It's very reactive stuff. And the problem with these di and trichlorosilanes is that they form polymers on the surface of the silica, and that can slow up your mass transfer by clogging your pores. So these days, basically, it's all monochlorosilanes that are used. Another alternative is to use an alkoxysilane but they're not very reactive, and there's really no way to catalyze them very well. So the game today is a monochlorosilane game. There are some exceptions. Okay, so now, if we think of R1 equals R2 equals a methyl group, R3 can be something like a C8H, what would that be, 2N plus 2, that would be 16, 18, so it would be C8, H17 would be an octyl, dimethyl octyl chlorosilane. Or another very common one is a C18, which would be H37. People have used C30 silanes. They've used a phenyl group attached through a propyl group to the surface, where R3 would be that. They've done this, where the ring hydrogens are replaced with fluoro groups. So this would be a pentafluorosilane, and it definitely has a different selectivity than that. And this has a different selectivity than that. And this has a somewhat different selectivity than that. Cyano. Now, this, of course, is not purely nonpolar. A cyano group is rather polar. But people do use these under reverse phase conditions. But this would also be used for normal phase liquid chromatography, where you're trying to make a somewhat polar stationary phase. Okay, so I can't tell you how many silanes are out there. There are companies that just make silanes, and they make hundreds and hundreds of silanes. They're a very important industrial chemical. I just mentioned the normal phase made with a cyano group, but you could also make a normal phase with an amino group. Now suppose you put this amino silane in water with acid. Then the amino group is going to protonate. It's going to turn into an NH3+, and now you have an ion exchanger, which is good for anions at low pH. At high pH, the proton comes off. It's not a very good ion exchanger. But you can quaternize that amino group by hitting it with something like methyl iodide and turn that nitrogen into a quaternary nitrogen, which of course has got a positive charge. And now you've got a strong cation exchanger. It's a strong base cation exchanger. You can attach a sulfonated phenyl group via a silane to the surface, and now you've got did I say cation exchanger here? I meant anion exchanger, because that's what's going to go on, come on and off, on and off. This is going to be a cation exchanger. And if you put something like a carboxylate group, now you've got a weak acid cation exchanger. So silane chemistry is incredibly flexible. Chromatographers should be very happy that organic chemists have developed all of these things, because they're utterly invaluable to us for doing all kinds of different sorts of chromatography. As we get deeper into this, you'll learn that on the surface of the silica, after it's fully hydroxylated, we go back to this, there are about 8 micromoles of OH groups per meter squared. So if you had 100 square meters, then you'd have 800 micromoles per gram. 800 micromoles is 0.8 millimoles. So you really have a pretty high surface concentration of these OH groups. But there's no way that you can, no one's ever figured out really how to totally functionalize the surface with a silane. And the chief problem is the surface gets crowded. If you had something like a dimethyl octyl silane, that takes up a fair bit of room on the surface. And the methyl groups and the octyl group don't let another silane with 2 methyl groups and an octyl group get onto the surface. So typically, maybe a little higher, maybe a little lower, 50% of these surface silanol groups get reacted. So you're doing pretty good if you wind up with 4 micromoles of silane on the surface per meter squared. If you had a big pore, like a 300 angstrom pore, you might get a little bit higher percentage covered. If it was a tiny pore, like a 50 angstrom pore, it'd probably be a lower percentage covered. Now, that means that the surface has got whatever silane you put on it, but it's also got some native OH groups left. And those native OH groups have different chemical properties because they're polar, because they are acidic. The OH of the SI is an acidic functionality. It's a lot more acidic than an alcohol. Methanol has a pKa of something like 15. Surface silanol groups have much lower pKa's. That means that the surface is really complicated, and we don't like that. So one of the things we do after we put on that on a surface, and we have an OH over here, we do what's called end capping, where we wash off we wash off the excess reagents and we start over again, and we would use something like trimethyl chlorosilane, which is a smaller silane. Some people will actually use dimethyl dichlorosilane, which is a little more reactive. And then what they're trying to do is get these residual silanol groups. Even so, you might get another half of a micromole per square meter reacted. You won't get much more than that. So there are still silanol groups left on the surface. They may be pretty well hindered at that point though, and other molecules may not be able to get real close to them anymore. And remember, most of the intermolecular interactions we're talking about drop off with 1 over r to the 6. So if you can keep the molecule from getting real close, the interaction's going to be pretty weak, or you hope it's going to be pretty weak. Okay, so yes.
Is it possible to use R3 as a very smaller, or as a smaller functional group, say a fluorinated methyl group?
No. No. A CF3 group sucks the electron density off of the Si like crazy, and it's going to go very rapidly. It's just not stable. That's why when I drew the pentafluorophenyl, I put 3 CH2 groups between the silane and that pentafluorophenyl. And even that's not all that stable. Okay, so we're still in the big picture now, make believe. You've gotten some kind of normal phase or reverse phase or what have you. We've got all kinds of possible stationary phases. Normal phase, acronym NPLC. Reverse or reversed phase, acronym is RPLC or RPC. The reason normal phase is called normal phase is because it came first. Michael Tsvet, when he invented adsorption chromatography back 1903 and 1904, the first materials he developed had very polar surfaces, and he used solvents like hexane, ether, stuff like that. Not very polar mobile phases. So normal phase means a polar surface and a low polarity mobile phase. Reverse phase is exactly the opposite. It means that the stationary phase is low polarity and the mobile phase is high polarity, like water, methanol, acetonitrile, or a mixture of water and methanol, acetonitrile, tetrahydrofuran, solvents that are fully miscible with water. And whatever you think about normal phase, the opposite is going to be true of reverse phase. A solvent that's strong in normal phase will be weak in reverse phase. A solvent that's weak in normal phase will be strong in reverse phase. A solute that sticks like glue to normal phase will come right off of reverse phase. It's very convenient. You get one straight and you got the other, but you better get the one straight if you're going to flip it around. I told you about ion exchange. There's all kinds of ion exchange materials. They're not all made out of silica. Some of them are made out of synthetic organic polymers. Of ion exchangers, we have cation exchangers and anion exchangers. We have those which use a weak acid or a weak base functional group, or those which use a strong acid or a strong base functional group. These acronyms are strong cation exchanger, weak cation exchanger, strong anion exchanger, weak anion exchanger. Another very important kind of liquid chromatography is what we call size or steric exclusion chromatography. People who are real chromatographers call them that. People in biochemistry or people in polymer chemistry will call them gel filtration or gel permeation chromatography. So this has got SEC, GFC, and GPC. They all mean exactly the same thing. It depends on who's doing it. It's that arbitrary. Affinity chromatography is a very interesting form of liquid chromatography. In affinity chromatography, it's also called bioaffinity chromatography. It's also called bioselective affinity chromatography, but I'm just going to call it affinity chromatography. What you do is you attach to the surface of your stationary phase some kind of biologically active molecule that binds very selectively to what you're trying to analyze for. For instance, you could take an antibody and covalently bind it to a surface, and that antibody will fish out very, very selectively an antigen to that antibody. Or you could take a coenzyme for a family of enzymes. For instance, nicotine adenine dinucleotide is a coenzyme that's used by a lot of different enzymes. You bind the nicotine adenine dinucleotide to the surface, and it will fish out the enzymes that bind to it in the act of performing some catalytic activity. You can't imagine the array of molecules that biochemists have figured out how to stick on surfaces and use to fish out very, very selectively the proteins, the nucleic acids, the whatever that they want. It's an extremely powerful biological analytical technique. Another related material is what we call metal affinity chromatography. It's also called ligand exchange chromatography. And let me go back to it. Good. So what we do here is we attach to the surface some chelating molecule. And we have this bind to some metal, but we deliberately don't put enough functional groups on the chelate to completely saturate and bind to all of the orbitals of the metal. So this metal is left with residual affinity for all sorts of things. For instance, if I put the right metal here, it will fish out only certain amino acids. Or it will selectively bind proteins that are very rich in that specific amino acid. And by changing the metal, we can induce different kinds of selectivities for binding different kinds of molecules. And they don't have to be proteins. They can be small molecules like amino acids. They could be specific drugs that happen to bind to a specific metal, so on and so forth. The last kind of chromatography I want to mention is chiral chromatography. If you want to separate two optical antipodes, two enantiomers, you have to use either an optically active stationary phase, or you have to add something to the mobile phase that's optically active. In either case, you're forming a transient diastereomer. Diastereomers have different chemical properties. They have different solubilities, they have different pKa's, they have different yada, 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 yada. So they will bind differently to the stationary phase, or they form the diastereomer in the mobile phase, and the two diastereomers interact with the stationary phase differently. There's a number of different chiral agents that have been used both as stationary phases and mobile phases. This is an exceedingly important field in the pharmaceutical industry. And in fact, most of the analytical work on optically active drugs is done by chromatography. Okay, so let's continue our overview of different kinds of chromatography. With NPLC, the stationary phase is the more polar phase. Typical normal phases are silica alumina, or silica that's been modified with a polar functional group, alumina that's been modified by coating it with a polar polymer, something like that. A typical solvent for normal phase, these are low polarity solvents, hexane, methylene chloride, ether. Isopropanol would be a really rather polar mobile phase to use in normal phase liquid chromatography. If I couldn't get my solute to come off of my normal phase, I'd work my way up to isopropanol as the eluent, and then maybe acetic acid as the eluent. and then maybe water as the eluent. But those would be immensely polar compounds stuck on that phase. The typical solutes for normal phase have to be at least somewhat polar. I mean, if you think you can retain hexane on a polar mobile phase and use hexane as the mobile phase, you're crazy. It's going to come right off. You've got to have some polarity in your analyte so that it will stick to the surface. Typically, they're organics, things like phenols. Typically, they have modest molecular weights. If you put in a polar polymer, it's just going to interact with the surface at so many points. You're never going to get it to come up off the surface. Sorry. Reverse phase, the stationary phase, is the less polar of the mobile and stationary phases. Charcoal has been used as a reverse phase material. C18 modified silica, alumina coated with polybutadiene polymer. Typical mobile phases: methanol plus water, acetonitrile plus water. Typical solutes. Now this is interesting. Reverse phase can be used for both nonpolar solutes and for polar solutes. You can retain benzene, which is a pretty nonpolar compound, in reverse phase chromatography. You can retain phenol, benzyl alcohol, benzoic acid, which are pretty polar compounds, in reverse phase chromatography. But you have to use the right mobile phase. You have to use a really, 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 really weak mobile phase, something that those compounds don't dissolve in very well, and you can get retention in reverse phase chromatography. Reverse phase is used for ionic and non-ionic compounds. They're used for low and high molecular weight. They're used for synthetic organic polymers like polystyrene. They're used for proteins. They're used for peptides. They're used for nucleic acids. They're even used to analyze carbohydrates under the right conditions. I've just told you why reverse phase chromatography is 80 or 90% of all HPLC. There are very few compounds that you can't do by some hook or crook in reverse phase chromatography. It's not quite universal, but it's a lot more applicable than normal phase chromatography. That's why it's the dominant mode. It also has nice features like the plate counts are really pretty good. Ion exchange, the stationary phase is ionic. The mobile phase usually has some salt in it, a buffer, something to hold the pH constant if it's a weak acid or a weak base kind of material. Typical stationary phases are sulfonated or aminated polymers. Your solvents are buffers and salts. You can do anions, cations. You can do low and high molecular weight chromatography. A lot of proteins are separated by ion exchange chromatography. A lot of nucleic acids are separated by ion exchange chromatography. Size exclusion chromatography. And I almost don't like to call it chromatography, because you absolutely don't want the solute to chemically interact with the stationary phase. This separation is driven entirely by entropy. When we get into, you hope it's driven entirely by entropy. And that causes the molecules to separate by size. It's used on inorganic and synthetic or natural, the stationary phase can be inorganic, it can be a synthetic or natural polymeric gel. When I say not natural polymeric gel, cellulose, agarose, are natural gels. Polystyrene, highly cross-linked polystyrene is a synthetic organic gel. The solvent used in size exclusion chromatography has to be very, very carefully chosen. It has to prevent any chemical interaction of the analyte with the surface. As soon as there's a chemical interaction with the surface, you're really doing either normal phase or reverse phase chromatography, and the analytes are not going to separate in order by molecular weight anymore. They're not going to separate by their actual size in solution. The lower end in molecular weight of size exclusion chromatography is about 1,000 Daltons. Molecules smaller than that, they're going to fit in all the pores and they're not going to separate. Any sizing gel has a maximum molecular weight also, where anything bigger than that molecular weight will not fit inside the particle at all, and all of them will come out together. There's a very distinct range in molecular weights that can be separated by any sizing material. In some ways, it's really difficult to do good size exclusion chromatography. Yes, Ryan?
Could you saturate the solvent with a salt to interrupt? If, for example, you were doing...
Yes, they will do that when they've got a protein and the stationary phase might have some charge on it, so they throw in a molar of some salt or other. But too much salt can cause hydrophobic interactions. It's too much of a good thing. Okay. Continuing the march. NPLC. The least retained analytes are your nonpolar. The most retained analytes are polar. A strong eluent in normal phase is a polar solvent. Water would be about the strongest eluent in normal phase. And a weak eluent would be something very nonpolar, something like hexane. Reverse phase, your least retained compounds are your most water-soluble compounds. So things that are strong hydrogen bond acceptors, because water is a very good hydrogen bond donor, not well retained. Something like glucose, not very well retained in reverse phase chromatography. Most retained solute would be nonpolar. The bigger that nonpolar molecule is, the more strongly it's going to stick to the stationary phase. So big nonpolar molecules. Naphthalene will undoubtedly be more tightly bound than benzene. Anthracene more tightly bound than naphthalene. If I had a homopolymer of polystyrenes, I guarantee you that the small ones are going to come out before the big ones. Your strong eluents are straight organic. They have to be water miscible. So things like water, THF, acetonitrile, isopropanol are very common solvents mixed with water. The weakest solvent in reverse phase is water, which is the most polar solvent that we use. That has a reasonable viscosity. Ion exchange. Least retained solute has a low charge and a large non-polarizable ion. Most retained have a high charge, or they're small. It's the charge to size ratio argument for ion exchange chromatography, modified a little bit by polarizability, because the charge can polarize the polarizable electrons. Strong eluent is a high salt concentration or a pH which removes the charge from the surface. So if, for instance, you had an amine, not a quaternary amine, but a primary or secondary amine as your stationary phase, and you raise the pH to 12, that charge is off of the amino group, there's no charge anymore, and your anions are just going to come ripping out of the column. Weak eluents are water without a salt in it, an alcohol without a salt in it, a pH that leaves the charge on the resin, on the stationary phase. Size exclusion. Your big molecules don't fit in the pores. They come out first. Your small molecules, your low molecular weight molecules, fit in all the pores. They come out last. The ones in between come out between the big ones and the small ones. It's really not fair to talk about strong eluents and weak eluents. You simply have to use an eluent that prevents any chemical interaction with the stationary phase. Normal phase. Stationary phase is more polar, mobile is less polar. Mobile phase, typical, hexane. Ethyl acetate is a beloved mobile phase among organic chemists because it's so nicely volatile. And lots of reasonably polar organics are soluble in ethyl acetate. We talked about some of these already. Again, mobile phase, water, very, very weak. Methanol, strong. Acetonitrile, strong. THF, strong. Ion exchange, we talked about. SEC. Yeah, let's do this. You got to use a porous solid. You have to stop the analyte from absorbing. Typical materials are silica. CPG is controlled pore glass. You might think that glass and silica are the same thing. That's absolutely not true. Silica is silica. Glass is a mixture of silica with something else like borates or phosphates. Controlled pore glass is a mixture of silica and borates, and these two materials, they don't mix well. So you have clusters of borate, you have pockets of borates and pockets of silica. Well, if you leach out the borates, you can make pores in a wide variety of pore sizes, all the way up to 2,000 angstroms. Various polar and nonpolar polymers are commonly used. Mobile phases are water, tetrahydrofuran. In the industrial polymer world, people will use dichlorobenzene at 180 degrees centigrade to dissolve the polymer that they're trying to work on, and do chromatography in that miserable solvent. And it takes a pretty good pumping system not to die in that. We talked about affinity chromatography, I think, enough already. We talked about ligand exchange enough. We talked about, well, let me give you an idea of what's done in chiral chromatography. Theoretically, if we somehow attach to the surface 3 very different functional groups in close proximity to one another, this material will exist in 2 forms. In one that rotates light one way and one that rotates light the other way. But you have to make the stationary phase out of one of those 2 enantiomers. This can separate a mixture of optical isomers. That's one way to do it. We'll talk about a couple more when we get a little bit deeper into reverse phase chromatography. The thing I just drew for you is what's called a Perkel silanized phase. People have put derivatized cellulose. Cellulose is a natural polymer that is inherently optically active. Mother Nature makes it that way for you. You derivatize it, and you coat that cellulose polymer on silica, alumina, what have you, and that, under the right mobile phase conditions, will act as a chiral stationary phase. There are a number of phases related to the really elaborate molecule called cyclodextrin. I'll show you what that looks like a little later on. There's a number of different chiral chromatographies. Okay. I think we're about ready for a break. Why don't we do that now?